What's up guys, this is Matthew Burns, and this is the second video tutorial covering registers in the series on how to build an 8-bit computer out of individual logic gates. What you see in front of you is the completed ALU for the computer, including the A and B registers for the ALU. These two registers, they're just, each one is made up of 8 positive edge trigger D flip-flops. It'll store 1 byte of data, and it holds the inputs to the ALU, which can add and subtract in binary. So, I remember in the last tutorial, I loosely used the term parallel when I was talking about the 8 positive edge trigger D flip-flops making up a register. Before I continue in this tutorial, I am going to show you what I meant by that. So, give me a second. It'll focus when I draw. When I said, I told you there are 8 positive edge triggered D flip-flops in parallel, and what I meant by that was that if we have more than one positive edge triggered D flip-flop, I'm not going to draw the setup out of NAND gates. I'm just going to show that there's an output, there's data, and there's an enable. And I'm only going to draw 2 of them instead of 8, but it's the same idea. You have an output, a data, and an enable. Can you see that? Almost. So what I'm doing when I say they're in parallel is I'm simply tying the enables together. So the enables are electrically connected. And so when you send a signal to the enable of one, you're sending a signal to the enable of another. So what you have is a device that has, in this drawing only 2, but on the registers, 8 datas, 8 queues, and 1 enable. And each data corresponds to 1 queue. And so you put a whole byte of information across the 8 data inputs. You pulse the 1 enable high, and Q will show that all 8 queues will represent the respective data inputs when enable was pulsed high, and will store that byte of data. So what I did here was I'm storing data on both of these registers, and I'm sending it through the ALU so we can see if the registers are storing data, and we already tested that the ALU is working. But I'm doing this in a fairly specific, kind of interesting way, just to test this out. So I have a constant value stored on this, and right now I think I have it set as 3, but when I demonstrate this I'm just going to put binary value 1 on this register, and binary value 1 will stay on this register for the whole demonstration. Register A up here is a little bit more interesting. I have the output of the ALU, which is going to sum these two together, which is going to sum the value in the 2 registers together, fed back to data of fed back to the data of this A register. So what's going to happen is, at first, this is going to be have a binary value 1. This here is going to have a binary value 0. And so this ALU is going to sum those 2 values together. And the sum through this black bus of wires is going to be visible on the LEDs. You'll be able to see what current values at the sum. What current value is the sum of what's in the 2 registers. You'll be able to see that on the LEDs. But also, it goes back to the input of the A register. So each time I pulse the A register enable high, this A register will accept the sum at data into the register. So then Q, which is now going to the input of the ALU, will reflect what the previous sum was, and now there'll be a new sum waiting at data for the A register. So each time I pulse the enable of the A register high, the ALU, or the A register, will accept the previous sum into the register, and a new sum which is 1 greater, will appear in the LEDs. So there was one problem I encountered while testing this, and that was that I could not just pulse, I couldn't just touch two, I was using wires as switches because I don't have switches. I couldn't just, this here's the enable wire, I couldn't just touch two wires together to bring it high. I had it pulled low with a resistor, and I was touching wires together to pulse it high. Because every time I brought the wires close together, there was, it wasn't a perfect low signal, high signal. I'll draw out what I mean here. When I touched the two wires together, which is a very crude switch, give me a sec. When I touched the two wires together, I didn't have a low signal and then a high signal. Instead, I had something kind of like this. And it was very messy when the two wires got closer. Maybe they bounced off each other a little bit, or maybe when they were extremely close together, maybe the air between them ionized and a spark jumped across or something like that. But the signal was really awful, and so each of these peaks the enable triggered, and so the thing would cycle like 100 times before it finally settled. So in order to solve that problem, I just used a SR NAND latch, which we talked about in the previous tutorial. I'm using an SR NAND latch to, I don't know what you call it, I guess it's debouncing maybe, but I'm just basically smoothing out that signal. So if I have, what I'm going to do here in order to I guess debounce or remove all the oscillations from the signal is I'm going to use this Q as my output. It's going to go to the register. And then I'm going to have a resistor pull each of these actually high. So same on the other side. And then what I'm doing is I'm just using a wire as a switch, but I'll just draw it as a switch in this to pull each of these low. It's connected to ground. There's my other switch. I have to make sure that's visible on the camera. And what I do is, this here goes to enable of the registers, and we talked about in the last tutorial that the registers will accept data onto Q when this is pulsed high. So, it doesn't matter whether I leave Q high or leave Q bar high. Just so long as when I push one of these buttons, switches, and pull, let's say I pull this input low by pushing that switch or connecting that switch and allowing an electrical pathway from this input of the NAND gate to ground. When this input's low, Q is going to go high, and then this Q bar here will go low. So then this will be pulsed high. When I let go of that switch, or when I open the electrical pathway, this SR NAND latch will see a 1-1, and this input will stay high. And so by having the SR NAND latch hold the Q high, even when this switch is closed again, or open again, I can remove all those oscillations. The only downside to this setup for debouncing the signal is that I have to push this button before I can push this again. So I basically have to push this button to trigger the setup that I have over there. Then I have to push this button to reset it. Then I have to push this button to trigger the setup again, and then push this button to reset it. But it's not much of a problem. And there's one other thing that I want to discuss in this tutorial before I demonstrate the registers in the ALU, and that is the system for enabling the registers. So I had this drawing up here before, just talking about how I had the enables tied together with Q, data, and enable. again, Q, data, and enable. And I talked about how I had enable tied together. There's one issue here that we're going to have that might not be clear now, as we haven't discussed how the computer is going to be set up, or what even makes a computer at this point. And we'll go into that in more detail when we talk about the control matrix and the ring counter and all that important stuff. But for now, I'm just going to tell you that the computer's clock is going to be a square wave. And the ring counter is basically going to be a bunch of, you don't have to know this right now, so this might be a little bit confusing. Or, I'm going to try and think of the best way to explain this. We need, on one clock pulse, to be able to put data on the data lines and accept the data. So from somewhere else in the computer, when a signal goes from low to high, we need to put data on the data lines, and we need to accept the data into the registers. The only thing is, if I pulse enable high at the same time I send a signal for other logic gates to release the signal to this data, you could see there might be a problem. Enable might be triggered before the data gets to the input of these positive edge triggered D flip-flops. And that would cause a pretty big problem. It would stop the operation of the computer. It wouldn't function properly because the registers wouldn't be receiving the proper data. And so I needed some way for, if here's the signal that's triggering this in the computer, I needed some way for data from anywhere else in the computer to be pushed onto the inputs of the positive edge trigger D flip-flop as soon as it sees a positive signal here, as soon as the signal goes high. And then I needed enable to wait a little bit. So what I decided to do was to build some sort of setup built into these registers, so that every time so instead of having a signal like this, if this is positive 5 volts, if this is 0 volts, every time the signal jumps high, this here will jump low, and then after a certain short amount of time it'll jump high again. And so, by doing that, if I have this signal here fed to enable, the data will be pushed onto the data lines right at the beginning of the signal, and enable will be pushed onto the enable will be triggered shortly afterwards. The only problem I had with that, which I'll show you the setup now, I had extra 3-input NAND gates on the bottom of these registers because each chip holds three 3-input NAND gates. So this here was the setup I used. I had this actually run to the enable. I had this be an inverted version of the signal, and I used a 3-input NAND gate. In order to use a 3-input NAND gate as an inverter, all the inputs are tied together, so if you have a positive signal here, that'll be low. If you have a low signal here, that'll be high. And I had these two wires connected, and this ran to the signal that we talked about up here. Well, what'll happen is initially when this is low, this here will be high, and so this will be a 0, this is a 1. So basically, in order to make a 3-input NAND gate a 2-input NAND gate, you just pull one of its inputs high, and it'll function as if it were just a 2-input NAND gate. So when I pulse this signal here high, this signal will go high right away, and because this logic gate has a certain propagation delay, a certain amount of time it's going to take for this to switch from high to low, for about 6 nanoseconds you'll see all 3 of these inputs high. And so what you'll see is, if this is your signal, right now the signal's high because this is low and this is high. When this signal here is pulsed high, it sees all 3 of them as high for about 6 nanoseconds before this middle wire here switches to low. And so 6 nanoseconds past when the signal jumps high, that's when it'll drop low. And then when this inverter slash 3-input NAND gate does finally switch to low, this signal will jump high again. And so you'll get a delayed signal where the positive edge is after the initial positive edge. And I use that to trigger enable. The only problem I had with this setup was that the propagation delay of one inverter wasn't great enough to accurately trigger enable every single time. Sometimes it would trip, sometimes it wouldn't. Sometimes it would switch multiple times. It just wasn't really functioning properly. So as a fix to this, what I did is I just tied this input here, well, output to this inverter, input to this 3-input NAND gate to power. And so now both of these are always 1. And this is simply an inverter. Whatever, it doesn't matter what goes into this. This is always high because I have it pulled to power. Whatever I put into this, if I put a 0 here, this will be high. If I put a 1 here, this will be 1, this will be low. And so all I'm doing is I'm inverting the signal going to the positive edge trigger D flip-flops. And so if this is the signal that will trigger the operations in the computer, this here is when data is pushed onto the inputs of the positive edge trigger D flip-flops. This here at the very end is where enable will be triggered. And so enable's triggered after data is pushed onto the inputs of the positive edge trigger D flip-flops, and that did solve my problem. So enough of that. I'm going to demonstrate the setup that I built over here. This is not how the computer is going to be hooked up, but I just thought I would test this to make sure that the registers were working properly, especially with that last minute fix with that jumper wire I threw in place to pull that middle input of the 3-input NAND gate high. So I'm going to supply power to this. I'm going to set the B input to B register to 1. Now that I changed the data for the B register, I still have to pulse enable high, otherwise it's not going to, otherwise it's still going to hold what it was previously holding. So now the B register is storing a value of 1. And there's nothing in the A register, or actually the A register at this point is probably all high, because a value of 255 plus 1 will show 0 on the 8 bits visible, because that would cause an overflow into the 9th bit, which we don't worry about. So this here, this chip there, is the 2-input NAND gate chip that I'm using to debounce the signal. This wire, I have to touch back and forth between those two resistors to set and reset the set reset NAND latch and enable the A register. So I'm going to do that now. If you look, the first red LED on the end lit up. I'm going to have to disconnect the camera from this tripod because that's not very visible. First one lit up. Second one lit up. And each time I trigger this enable here, by switching those wires, another one is lit up. And so, our ALU is adding, and our registers are storing data. So that was it for this tutorial. I just wanted to show you how I had the enables of these registers set up, and that the registers do in fact store data and are functioning properly. In the next tutorial, by the time I record, I'm going to have 16 registers soldered together, and that will comprise the memory unit for our computer, where we will store the code and any data, any memory that we want to store. So I'll be going over that and probably the multiplexer we're going to use to point to one piece of data or one register at a time in order to make this computer function. So I'll be going over that in the next tutorial. For now, thanks for watching, and I'll see you guys next time.